Welcome to the first video of Chapter 14. Chapter 14, we're going to start looking at functions of multiple variables, and we're going to jump into some derivatives. So the big point of this unit is going to be partial derivatives, and then we're going to end the unit with some applications. Like most beginnings of the unit, we're going to start with some basics. So what is a function of 2 or 3 variables, and we're going to look at some graphs. So starting with what you did before, you've seen something like f of x, which is a function in terms of one variable. You have one variable, which your input is y. So here's an example. It's not written in function notation, but we have our dependent variable y that is in terms of one independent variable x. What we're going to be looking at now is functions of 2 or more variables. So here, z is a function of x and y. So z is our dependent variable, and it depends on both x and y. So for example, area of a triangle. Area of a triangle is based on the base and height of the triangle. So writing that in function notation, our area, which is our function, is a function in terms of base and height. So for z equals f of xy, z is the dependent variable. X and y are the independent variables. And we can have functions of more than 2 variables. So for example, in 3 space, we have some variable, let's call it w, that's a function of now x, y, and z. What we're going to look at next is domain. Domain are the restrictions on the independent variables. So let's take a look at an example. Example 1, find the domain of f of xy is equal to the natural log of xy. Okay, well, geometrically, we know the argument, or not geometrically, algebraically, we know that the argument of a log has to be greater than 0. So we know that xy has to be less than 0. So there's a few different ways that we can express this domain. Firstly, it's good to just look at geometrically what this is referring to. So if we're looking in 2 space, which is all the points of x and y, where do we have a product that's greater than 0? Well, if both x and y are positive, the product will be greater than 0. If both x and y are negative, the product will be greater than 0. So this is one way that we can express the domain, is that graph. Second way is we can express the domain in words. So our domain is all ordered pairs in quadrants 1 and 3. We are not looking at the points, though, on the axis. And that's because our points on the axis would give us a product of 0. And then thirdly, algebraic notation, our domain is all x and y such that xy is greater than 0. So on WebAssign, you're going to see domain in a specific way, but in your packet or on a test, you can use words or you can show a picture, either one. Okay, so then our second example, we're finding domain again, except this is a function of 3 variables. So we have a fraction, that x in the numerator we don't care about, that doesn't affect the domain. But in the denominator, we know 2 things. We know that that quantity that is underneath the square root has to be greater than 0. Can't be 0 because then we would end up with 0 in the denominator. So the quantity underneath the square root at least needs to be 0 or positive, but then we take out 0 because we don't want 0 in the denominator of the fraction. So solving this or making it look a little bit more friendly, this is the same as x squared add y squared add z squared is less than 9. So if we want to express this domain officially, we can say that our domain are all points x, y, and z such that x squared plus y squared plus z squared is less than 9. Or secondly, if we want to put this in words, if we were to graph this, this is the set of all x, y, and z inside the sphere of radius 3 that is centered at the origin. And again, we're not including the points on the actual sphere itself, only the ones inside the sphere. And then secondly, I could ask you something like find f of 2, 1, 1. If you were asked to do that, you're just going to plug in 2 for x, 1 for y, 1 for z. And so you would get 2 over the square root of 9, subtract 4, subtract 1, subtract 1. And so our f of 2, 1, 1 would be 2 over root 3. Okay, so that is the basics or the start of what is a function of multiple variables. How do we find the domain? So the next thing that this is going to lead us to is graphs. So if we look at z being some function of xy, that gives us a surface in 3 space. And so we have 2 examples that we're going to look at. This first example, what I would suggest is f of xy, I would just change that to z. So our z is dependent on x and y. So this gives us z is equal to the square root of 4 minus x squared minus y squared. And you might be able to see that right off the bat what that is. What you might find helpful, if you don't recognize it immediately, is to square everything and put x and y on the same side. And so this is what we get, x squared plus y squared plus z squared equals 4. And so if we review, this is a sphere where the radius is 2, and it's centered at the origin. But now we need to go back and look at our original function and make sure, is that what we're really graphing? Are we graphing the entire sphere? Well, what we see when we go back is that this z is equal to some square root. So that tells us that z has to be positive. Well, it has to be 0 and bigger. We're not going to get a negative number out of that square root. So what does that tell us? We're not looking at the whole sphere, we're looking at a hemisphere. So if we were to go graph this, hemisphere where the radius is 2, forgive my drawing skills, you guys know that this is not my forte, so I appreciate your kindness in not judging my hemisphere. So there we go. Okay, so the next one, f of x, y is equal to 1, subtract x, subtract 1/2 y. This is linear, so linear x, linear y, that tells us we're looking at a plane. Best way to graph a plane, or probably the easiest way, is to find the intercepts. So find x when we make y and z 0, find y when we make x and z 0, and then find z when we make x and y 0. So I already found those for you. It's 1, 0, 0, 0, 2, 0, and 0, 0, 1. So then the way that we're going to graph this, our 1, 0, 0 is here, our 0, 2, 0 is here, our 0, 0, 1 is here. So it gives us this portion of the plane. So that's what's really important, is this is only a portion of the plane. It's really hard to draw it continuing, but we need to make sure we understand that this plane does in fact continue. Okay, so what we're going to move on to now is something called a level set, or a level curve, or a level surface. So here's a definition. The level curve of a function of 2 variables are the curves with equations f of xy is equal to k, where k is a constant. Okay, so you have a few different examples here. Let's look at the example on the left. So what's going to happen is you're going to have some z is equal to f of xy. And that's what you see in blue. So then to get all of these level curves that you see, you take that f of xy and you set it equal to some number. And that gives you what is called a level curve. So what you're doing is when, let's say, let's pick f of xy equals 20. What we're doing is we're cutting a plane through at k equals 20, and we're taking that resulting circle and reflecting it down onto the xy plane. And that gives us what's called a level curve. So then the question, of course, is going to be, why do we care? Why do we care about these level curves? Well, if you look at something like the set of level curves or that map on the right, so what you see on the right is just the level curves. So it's the level curves of a mountain. So let's say that you graphed the mountain and you sliced a bunch of planes through it. These would be the resulting level curves on the xy plane. And so what can we tell from this map? Well, if we're at point B and we're traveling to point A, we might want to know what's going to happen. What's going to happen as we're traveling on the mountain? Well, what we notice is we're at an elevation of 5,500. As we go to A, and as we keep going, we get to 5,000, 4,500, 4,000. So if I asked us, when you're at point B and you're moving towards point A, what's happening? You're going down the mountain. That's how we use these level curves. Okay, so let's look at an example. Example 4, describe the level curves of z equals x squared plus y squared. So before we even do that, let's review what does this look like. So if we were to graph this, hopefully we recognize z is going to be positive, and this ends up being a paraboloid. So then we have to picture passing various planes through or making z a number. So we might make z equal to 9, and then we might make z equal to 6, and then maybe 4, and so on and so forth. There are infinitely many. So if we were to make z9, for example, we get this circle, and then we get another circle just with a smaller radius. So when we reflect those onto the xy plane, we're going to get these level curves that are circles. So that right there is the set of level curves. So if we were to describe the level curves, we would say the level curves are circles centered at the origin. So then if we think back to that map, what that map looked like is it was the set of level curves. It was all the level curves, or many of them, graphed together. When you do that, so when you put all of the level curves together, it's called a contour plot. So a contour plot is the set of level curves. So if we want to draw the contour plot, or a set of level curves for that paraboloid above, it's going to be in the xy plane only. So we would have a circle of radius 1, we're going to have a circle of radius 2, we're going to have a circle of radius 3, and oftentimes they will be labeled. So here's where z is 9, here's where z is 4, here's where z is 1. And again, how we use this. If you are at this point here, I might ask you, as you move out, what happens? Well, as you move out, z is getting bigger, so you're moving up the graph. You're moving up vertically. On the other hand, if you're here and you move in, you're moving down. You're moving closer to the origin, or you're moving down in terms of z. So that was a pretty simple one with just some circles, so let's look at one that's a little bit more complicated. We are going to sketch the contour plot of f of xy is equal to x squared subtract 4y squared. So what I would suggest to you is just pick some convenient values of z. So if we choose z equals 0, that's going to give us x squared is equal to 4y squared. So y then is equal to plus or minus 1/2 x. So what I'm going to do then is, before I keep going, I'm going to graph that. Okay, so here we get one where z is 0. That's our positive 1/2 x. And we're also going to have our negative 1/2 x. Okay, I can tell you another one that's going to be convenient is z equals 4. So when we do that, we get 4 is equal to x squared subtract 4y squared. If we divide by that 4, we get 1 is equal to x squared over 4 subtract y squared. Okay, so the question here is, what does that look like? This is a throwback to something you hopefully saw in Algebra 2. This is going to be a hyperbola. Okay, so here's what we know about this hyperbola. First thing we know is that because it starts with x, it's going to open on the x-axis. And because of that 4, we go to x is 2 and x is negative 2. And then our hyperbola is going to open to the left and to the right. So that blue one is when z is 4. And then let's do one more. What happens if we make z a negative value, like a negative 4? So we're going to have negative 4 is equal to x squared subtract 4y squared, which gives us 1 is equal to y squared subtract x squared over 4. So this is again a hyperbola, but it's going to open up and down. Okay, so if we look at that y, this time we're only going up and down 1, and then going from there. So that green is where z is negative 4. And hopefully you should see the pattern here. As z becomes more positive, we're going to be moving along the x-axis. As z becomes more negative, we're going to be moving along the y-axis. And so a few things that we should be able to tell is if I'm at the origin and I'm moving right, what's happening on the graph? Well, if I'm moving right, I'm getting higher and higher and higher on the graph. I'm moving up vertically. If I'm here on the graph and I move in the positive y direction, what's happening? Well, I'm going down. Z is getting more and more negative. And so the question, of course, then becomes, what is this graph? If we were to actually graph it in 3 space, what would we see? We would see a hyperbolic paraboloid, aka the graph that looks like a saddle. Okay, so these are contour plots or level curves when we have a function of 2 variables, a function that we can graph in 3 space. What happens though when we have a function of 3 variables? Well, that's where we're going next. Okay, so a level surface. A function of 2 variables has a surface that we project as level curves. So what that means is, in this previous example where we had f of xy is equal to x squared subtract 4y squared, when we chose a z value, whatever it was, it gave us a curve in 2 variables. So something that we could graph in 2 space. Because we graphed it in 2 space, it's called a level curve. Well, on the other hand, if we have 3 variables in our function, then we have what's called a 4D graph. So then what we get for our level surface is going to be something that's graphed in 3 space. Okay, so for example, let's look at example 6. Describe the level surfaces of f of x, y, z is equal to x squared plus y squared plus z squared. We can't graph this, right? If we were to graph this, this would be graphed in 4 space. This is some variable, maybe w. So we can't graph this. This would be graphed in 4 space. So if we're looking at the level surfaces, we're taking this function and we're making it certain values. We're cutting values through. So maybe we choose that value to be 1. Maybe we choose that value to be 4, maybe 9. And so what we get is we get something that we graph in 3 space, which is why it's called a level surface and not a curve. It's a surface because it's graphed in 3 space. So if we were to describe these level surfaces, we would say that the level surfaces are spheres that are centered at the origin. And just a fun fact, again, we're going to ask what's happening on this graph. As the distance from the origin increases, so does the value of f. So what we're saying is as we get farther and farther away from the origin, the function value is actually higher. Okay, that is the end of the required part of this video. I'm going to end this video graphing hyperbolas or doing a review of graphing hyperbolas. If you know how to graph hyperbolas well, you can stop here. If you don't and you want a quick review, please stay on with me. Okay, so we're going to do 2 real quick. This first one, few pieces of information. Whichever direction is the positive direction tells us which way we open. So this is going to open on the x-axis. Okay, so if we start with that. Square root of 9 is 3, so we're going to have to go 3 in both directions. The part that I skipped over earlier is how do we know the magnitude or the slope of the way that this hyperbola is going to open? Well, our slope is going to be plus or minus b over a. B is the number that goes with y, so this will be plus or minus 4. A is the one that goes with x. So that is going to be the slope that our hyperbola follows. And by slope, I mean the slope of the asymptotes. Sorry, I know this is not super accurate. So then, lastly, to finish out this hyperbola, go from those 2 points that we have, and you're going to follow along these asymptotes. Okay, so we're going to do one more, and you see it to the right. So this one opens up on the y-axis, because y is positive, to find our slope, plus or minus the value from y, then the value from x. So here is going to be one asymptote. There's going to be the other one, and then our hyperbola will follow our 2 asymptotes. Not asymptotes. I'm sorry. I should not have used the term asymptotes. They're not asymptotes. Let me be clear with that. They're not asymptotes. They just help us find the value of the graph, or the direction of motion. Okay, thanks for sticking with me. I will see you in class.